So in this video, I'm going to talk about the Bayes variance decomposition. As you may already heard a lot of the words, a lot of times I talk about the underfitting, overfitting. Actually, how to evaluate that underfitting, overfitting is come from the Bayes variance decomposition. Okay, so now let's see a little bit more in details. So here in the following, I talk about hypothesis. Hypothesis H. Here I mean some models. For example, linear regression, polynomial regression, with construct the base features. Okay, so actually there are two sources of the errors given a model you choose or given a hypothesis. So there are two sources of errors. In a hypothesis. H. Okay, so the first error comes from the Bayes, because in reality we do not know what's the ground truth function. So no matter what function model you choose, there are some Bayes between the models. So the Bayes here, what I mean is the error due to the inability of hypothesis H to fit G perfectly. Okay, for example, suppose, so here is one example I'm gonna show you. So here is an example. Suppose the ground truth function is this sine curve, but with a linear trend. Okay, this is the truth function. Ground truth, but the hypothesis is we assume some linear function. So the hx here is just a plus bx linear function. So no matter how good your algorithm is, how you gonna find these parameters in this hypothesis model, because you assume it's a linear model. No matter what you do, there will be some Bayes. For example, at any point x, there will be Bayes. So the Bayes is between this model and the ground truth model is called the bears. It's called bears. Okay, and the second error source is the variances. Variance. So this is the error due to fitting random noise. In data. So in this example, I can give you another example. Suppose we have a model. Suppose the ground truth is a linear model. Okay. Suppose the ground truth is Gx. Ground truth is a plus bx. So for example, we have the suppose this is 5. So suppose this is 5 plus slope is 2x. Okay. Suppose this is ground truth, and we generate data. When we observe data, we don't observe this gx directly, right? We observe the gx plus error terms. So each time we simulate data along this this line, so we have our true observations will be like this. But every time when we do the estimation, no matter how good your algorithm is, so we may our fitted line cannot be exactly this h, this g, right? This is a fitted line, predicted curve. So no matter how accurately we can estimate it, this hx can never equals to exactly this gx due to the random error noise. So this is called the variances. Okay. And next, I will give you some formulas that can decompose the squared error loss into this biases and variances. Okay. Let me write down here. I need more space. Okay, again, let's recall the assumptions, assumptions for the model. So we have our features simulated from some distributions D. Okay, we have some errors epsilon I generated from some distributions with average 0. You can think this is the normal 0 sigma square. You can also think this is maybe xi from the uniform distribution on with some range. This is just example. Okay, and our observed y is generated based on the assumption we have the ground truth function g and xi plus some error terms. And the goal, we find fit some pre-assumed model. For example, we don't know what the g is as a linear sine function, complicated function g, but we assume we want to use some regression. For example, the linear regression, polynomial regression, logistic regression to fit our data to our observed data x and y. Okay. Actually, note here, h will be a function of x and y. H is a function of random data. Is a function of random data. So, therefore, h is also a random variable. So, for example, based on one simulated data, suppose we can estimate h is this line, okay? And we simulate data again, we get another data, we get this line. And the third time, we estimate data, we get this third line. So each time we get a slightly different h. So h itself is a random. Is random. Yeah, this is important. Think about this one, this idea. So now consider. So we want to consider some point z. Okay. So at each point z on the feature space, consider arbitrary point in the feature space. Suppose we have the d-dimensional feature space. So it's not necessary to be a sample point. Sample point. So which means z may not be in this X set. So and we wanted to see. So assume this. Therefore, so z is a fixed value. Okay, and we have this gamma. Suppose this is the true value. This is g z plus epsilon. Okay, with this epsilon simulated from same epsilon as this one. So epsilon simulated from d prime. Okay. So actually, this expected value of this gamma equals to, because this z is fixed, so this is true fixed constant. So expectation is just the gz. Okay. Epsilon its average is 0, so this is just the gz. Okay. And the variance of this gamma equals to variance constant. There's no variance, right? And the variance of the epsilon. So in other words, we want to check what's the mean squared error loss at any fixed point z. Okay, so next the plan is we want to find the okay, so and here we assume the risk function is a squared error loss. when loss is squared error. Okay, so therefore we have the RH, the risk, a risk of some pre-assumed function is just the expected value of the loss function between the predicted value at z and this gamma. Okay, so in this case, h is a random variable, gamma is random. So h is random. Gamma is random. Okay, so the expectation is over possible sets, training sets. X, Y, and gamma. Okay, X, Y you can think is observed value. Gamma is gamma is a predicted function value at the fixed point z, fixed point z. Remember that our h is a random variable. We are taking the mean over the probability distribution of the hypothesis. Remember that the training data x and y also come from the joint probability distribution. We use the training data to choose the weight. So the weight defines the function h. If we assume this hypothesis is linear function, so this weight a and b is determined by this x and y. Okay. It may be hard to work out this directly, this distribution, but this just is some notation, So, and then now next we're gonna simplify this, calculate this risk. This can be written as, actually, if we assume the loss is a squared error loss, so we can have the expected value of hz minus gamma square loss. Okay, and this is equals to we can expand the square, so it's hz square. So it's a predicted value at z minus 2 times expected value of gamma and hz. You can think this gamma is you can think this is gamma is gz, right? Plus epsilon, plus some error term. So you can think this is a true predicted value, a true value at this z. Okay, and plus expected value of this gamma square. Okay, actually, since gamma and h are independent, because when we simulate gamma, the gamma is generated from the true function g plus some error term epsilon, and h is determined by the estimated from data x and y. So gamma is independent with h and z. Okay, So you can think this gamma is before we get there is some ground truth g function is predetermined there, right? We want to estimate this g. So at that time we already observed the g z plus epsilon. So we get this gamma first, and then once we generate data, we can estimate this h, and then we plug in this z, fixed value z at h. So we observe this h second, predicted value second. So you can think this is they are independent. If they are independent, so this means this expected value equals to the gamma expected value of the hz. Okay, expected value of gamma okay. So therefore we can write down the middle term into the predicted value of the two expectation. This due to the independence. If we have two random variable, maybe I give you a little bit lemma here. If we have random variable x and a variable y are independent, this implies the expected value of the product equals to expected value of x multiply the expected value of y. Okay, so we just use this one, and so now this square term are hard to calculate, so we want to write it down using the variance term. Maybe let me recall you the variance. Variance of the x random variable is equals to a squared error expected value square term minus the first expected value square. If you check any statistic or probability textbook, you will find the variance formula like this one. So it's expected value x give a square. Okay, so that's how we define the variance. So the first term we can written as a variance of the hz. And plus expected value of hz square. Okay, and plus, so this is the first term, right? Second term, the gamma expected gamma square we can also written as a gamma square. Variance of the gamma, variance of the gamma plus expected value of the gamma square, and minus 2 times expected value of the gamma expected value of the hz. Actually, these three terms actually complete the squares, right? So we can have the variances of the hz plus the variances of the gamma plus these three terms add together, we can have the expected value of the hz minus expected value of the gamma square. Okay, so now you're gonna see what we are doing here. So we have the variance of the hz, okay, plus the variance of the gamma, because gamma, since gamma equals to the gz, right, plus epsilon. So, and the variance, this is the constant, the function value at unknown truth function value at this point z, and the variance comes from this epsilon. So the variance gamma equals to the variance of the epsilon. and plus, so what's this term? This term equals to hz, right? Expected value of hz minus expected value gamma. Expected value gamma, remember epsilon has an average 0, right? So the expected value is just the g of z, okay, square. So actually what's this? This is called the Bayes of H of your model, okay? This is the variance of the model. This is the Bayes of the model. And this is an irreducible error term. Irreducible error, okay? So now we written our risk function into the 3 terms. So in other words, we write down the risk function as the 3 terms. Here, right. So here we can use this plot to demonstrate this, where these 3 terms come from. So the first term is the variances of this hz. So in other words, so the variances of the your function, suppose here our function is just a simple linear regression function. This variances tells us, suppose we simulate data from the ground truth, how much variations each time we get the line. Okay, so this is called the model variance. And the model Bayes, we already talked about, is just the distance, for example, at the fixed point z. What's the distance between the h? So this red line is h, right? This I'll write down here. This red line is h. This red line is h. This value is hz. Okay, this curved line is our ground truth, right? So it's the ground truth at z. So this difference is Bayes of h. So no matter how you fit the data, what algorithm you use, the differences between the ground truth and your proposed function. So this is called Bayes. And also we have the irreducible error term. So when you simulate data, your data is your gamma is equals to the ground truth at z plus epsilon term. So here we can think this is this is g at this point is gz value. So this difference is called variance of the epsilon. Okay. So no matter how accurate measure you're gonna take, there are some small errors for the observed data. So this is called noise errors. So this is called the variance, Bayes variance decomposition. Okay, so this is called variance. Oh, Bayes variance, sorry. Decomposition. So now, we know this Bayes variance decompositions. Actually, let me show you another plot here. Actually, this can be used to evaluate how good our model is. So, which means you cannot only check the errors on the training data set. I will summarize some summaries. Maybe I will give you in the next video.